Now moving into a talk from Xun Shi on a high-throughput computational approach to environmental health study based on CyberGIS.
Thank you very much. Thanks, Mike. It's an honor to be introduced by you. And first of all, I apologize for dressing up. I realize I'm the only one in the room doing that. And I told Shawan this morning I'm always the only one who going the opposite of the room. I learned this lesson in the conference in health and medical. Most of the people in the audience were medical doctors. And they dressed up, and I was not. And make it very obvious who's the geographer in the room. And this time I go to the other opposite. I consider the privilege to give this talk right after Mike and Shawan's grand overview of CyberGIS. I hope my talk can provide an example to some items covered by the grand overviews. Because a message I got from, say, Mike's talk is that at this stage, CyberGIS is looking for applications, looking for new discoveries, new problems, new decisions in the predictions. And on the other hand, certain applications are looking for new tools, new methodologies, new technology like CyberGIS to see if they can be solved or maybe resolved in a better way. So I hope this talk can provide a kind of example, a specific example, some items in that aspect. I might be one of the 5 million new users, as Mike said. I've officially got involved in this area maybe exactly 1 year ago in the conference, in the GI Science Conference at Columbus, Ohio, last year in September, and I had a kind of a chat with Shawan, and he grabbed me into this area. And since then, I have been learning about CyberGIS, and literally Shawan gave me some private lessons about what CyberGIS is, and I put this as my very first slide actually, and to show how much I learned, and this from the notes I took from those private lessons. So these are some basic functionality of CyberGIS. I think it might be related to the application I'm going to present, and I can see there are three basic functions can provide by CyberGIS. First, accessibility, which is CyberGIS can provide access to many users to certain GIS capabilities, especially those advanced and intensive capabilities that may not be really available to many normal users. And the second, computational capability. And CyberGIS can provide, because it can take advantage of cyber infrastructure, and so it can integrate or deploy the resource and the functions to many different CPUs and resources, so enhances computational capability in handling intensive operations and big data. And third, CyberGIS can provide the management capability to really cooperate different uses from different users to achieve or enhance or improve interoperability among different users. So I consider this might be some functions provided by CyberGIS and might be related to the application I'm going to present, which is environmental health studies. And among the three, in this talk, I'm going to emphasize on the second one. We are still working on, actually we're working on all of them, but at this stage we think we have achieved something on the second one, so I'm going to focus on the second one, the computational capability. So the application I'm going to present is the environmental health study or spatial epidemiology. And the approach I'm going to present that can take advantage of CyberGIS may lay in three aspects. First, it's a process of disaggregating polygon level location data. And I'm going to use this is a process called, I call it a restricted and controlled Monte Carlo process to disaggregate polygon level data to kind of approximately point or individual level. Second, this process includes a process of calculating local statistics. For example, a kernel density calculation for each location. And third, we use a very intensive process, Monte Carlo process, to estimate, to evaluate statistical significance. So these three aspects might be something that this approach can take advantage of CyberGIS. First of all, the disaggregation. So in most health studies, the data we got is at the aggregate level, at the polygon level, and the area unit level, something like this. So we have this number of birth defects in this polygon. This polygon is a town. It's represent the town. And we have this many total birth in this town. This is data we got in environmental health studies in most cases. However, to use the data aggregate level might be disadvantages, may reduce the quality of the study, and there's many studies on this. As a geographer, we are all familiar with this. The map at the polygon level has many problems, and if we can disaggregate them, might be able to improve the quality of the analysis and also evaluate the uncertainty. So what do we want to achieve is like this. We want to disaggregate the aggregate level, area unit level, polygon level data to individual point level. So those red dots on the right map indicate the disease cases. Those green dots represent the normal cases, normal birth, which is the background. And that grayscale map represents a detailed population distribution. So we want to take advantage of the detailed population distribution to disaggregate our aggregate level data. And I use a process called restricted and controlled Monte Carlo process. So in this process, first assign polygon level address to random locations. And this randomization is restricted by the smallest possible polygon to which a polygon level address belongs to. For example, town polygon or zip code polygon. And this randomization is controlled by the detailed background data, for example, detailed background population data, for example, land scan data, and the very detailed census data, for example. So this is why it's called restricted and controlled randomization. And we repeat this process many times to evaluate the uncertainty in this process. So this is why it's called a Monte Carlo process. And the advantage of this process, I summarize the advantage of this process first. It allows analysis designed for individual and precise locations to be conducted. For example, the kernel density process can be conducted, can be performed for those data. And second, it maximizes the utilization of available spatial information. For example, use the smallest possible polygon to restrict it. That actually maximizes the use of the polygon the spatial information in those polygons. And also we take into account any available information for the detailed population to maximize the information in spatial information in those data. And finally, we can through this process, through this many repetition, through the Monte Carlo process, we can explicitly evaluate the spatial uncertainty caused by the imprecision in the data. So this is the first one. Use RCMC process to disaggregate. The second, to calculate the local statistic. To estimate, for example, to estimate the local disease intensity, to see if a place has a higher intensity of the disease than other places. And very commonly used statistics, the kernel density. And essentially, we want to calculate for each location the ratio between the disease cases and the cohort. And one thing is the kernel density calculation in disease mapping. In this mapping is different from the conventional one because it needs to consider the background, the background population, the cohort. And so this is basically the ratio calculation between the disease cases and the cohort. And for this purpose, we distinguish different types of bandwidth. For example, the bandwidth of the kernel density can be fixed like this, which means apply the constant fixed bandwidth to every location, or can be adaptive to local situation like this. And can be what they call the side kernel, which means we put the kernel at each side. In the raster, we put the kernel around each cell for which the kernel density is going to be calculated, going to be estimated. I call the side kernel. And the kernel can be put just around those cases. This difference might be important and might be overlooked before. Actually, over a homogeneous background, these two types of the side kernel and case-side kernel, they will generate exactly the same output. If we don't consider any background, then these two methods, actually, the two bandwidths are actually equivalent. But if we calculate kernel density over the homogeneous background for the population distribution, then they are going to provide these two types of bandwidths are going to generate different results. And the difference can be pretty considerable. So by combining those the 4 types of bandwidth, we have 4 types of bandwidth, and the results from them can be pretty different. Anyway, this is the estimate of local statistic. And the third stage is to estimate the significance, statistical significance we can use. So first of all, we used RCMC to disaggregate the data and calculate the kernel density. And this generates a result of we can consider the actual spatial distribution of the disease. And we want to evaluate the significance of density value or intensity value at each location. And we use an unrestricted Monte Carlo process, which means we disaggregate the disease case data and cohort data through a Monte Carlo, through a randomization process, but this time it's not restricted by the polygon. It is only controlled by the background. So I call it unrestricted but still controlled Monte Carlo process. And this process generated, we can consider as a random or maybe HO scenario of the spatial distribution of the disease. And then we can compare this random distribution with the actual distribution. And we repeat this many times, we can get a p-value. We can get the estimate of the statistical significance of the actual intensity disease value at each location. So final output can be a p-value map and showing the statistical significance of the intensity at each location, the intensity of disease at each location. So this is the whole process of this computational approach for disease mapping. In this process, there's a typo there, the 2 should not be there. In disease mapping, we also need to consider confounding factor, and these tables shows that the male people and the different age of the people may have different risk for certain disease, and to consider that, we need to consider the confounding factors, and basically we apply the process I just described to each age sex category, and then we integrate the results from each individual category to generate the final overall map. And from the RCMC process, we repeat many times. Actually, we generate many sets of with assumed actual distribution of disease cases. So the p-value maps I just presented through this process is just one single p-value map. Through RCMC process, we are going to generate many that p-value maps, and finally we can calculate the mean p-value for each location and use this as a representative p-value for each location. And we can calculate standard deviation or variance from that many p-values. And this can be a representation of the uncertainty caused by the data aggregation in the original data. And with these two maps, we can identify certain hotspots. For example, we can use that the mean p-value plus 2 standard deviation, and if it's still smaller than a specified threshold, then we can consider those locations at a high risk but low uncertainty. And we can consider those hotspots where we can perform further investigation, most interesting area we want to look into. Okay. The process just described is for disease mapping to see if a location is disease risk is higher or lower than other places, that disease mapping process. Another task in spatial epidemiology or environmental health is to detect if the spatial distribution of a disease have any association with the spatial distribution of certain environmental factor. And the disease environment association, spatial association, that's another task in spatial epidemiology. And based on the RCMC process for disaggregation, based on the UCMC process for evaluating the statistical significance, we can also create a methodology to do a simulated case control study. Case control study is a very conventional methodology in epidemiology to identify the association between disease and a certain factor, certain etiological factor. And with that RCMC and UCMC process, we can use spatial analysis, we can use GIS to do a simulated case control study. For example, for this location in the middle, we can, first of all, this background grayscale map is a raster layer of certain environmental exposure. For in this very specific cases, is the arsenic concentration in groundwater. This layer was generated by USGS. So this, then with the RCMC process, we can generate individual location of cases represented by those red dots. And with the UCMC process, we can generate individual locations for controls. Then we read the environmental exposure values at those cases and the controls. So we basically get two groups of exposure values, one for cases, one for controls, around a certain location. Then we can compare these two groups of exposure values if one is significantly different from the other. Say if the exposure values for cases is significantly higher than exposure values than controls, then we might lead to think that this environmental exposure might be related, might be associated with this disease. So this is basic idea. Okay, then we can do this for every location in your study area. Then output can be a p-value map. Again, can be a p-value map. And this p-value map means at each location, if the exposure values for cases is significantly different or higher or lower than the controls. And this shows the spatial variation in disease environment association as a map of p-value. So this is another task. The first, I basically just presented two processes. First is for disease mapping to show the spatial variation of the disease distribution. A second is for detecting spatial association between disease and environment. So there's two kind of separate tasks. And both can be based on RCMC and the UCMC process. So I just very quickly went over this kind of approach or methodology or technology in spatial epidemiology for the two tasks. First, the disease mapping. Second, the detection of the spatial association. Then the purpose I presented those is that I think this approach can take great advantage of CyberGIS. And especially at this stage, we're working on the computational capability, computational demand of this approach, because this is highly computationally demanding approach. For example, the number of iterations for calculated local statistics, for example, the kernel density estimation. Say, if this is a scenario, we have the stratification for age and sex for the confounding factors, and we have case data at the polygon level, we have the cohort data at the polygon level, and we also have the detailed population data. If this is a scenario, then this is the demand to computation. For the RCMC iteration, we only use very small number for the parameters. We have only two age-sex categories. We want to randomize the RCMC process. The iteration of randomization RCMC process is a very small number, just 100. And for the cohort, it's also 100. Then basically we need to calculate 20,000 raster layers of kernel density. And for the UCMC process, same thing. if just some very small number of parameter values, we got a very large number raster kernel density layers to calculate. Second, for comparison RCMC results and the UCMC results to estimate the statistical significance, and this comparison also requires a very large number of raster layers and calculation to do. And third, for the local statistic test, so suppose this is a scenario and we want to calculate a very specific kernel density calculation, and because this is pixel by pixel calculation. And at each pixel, the operation is already intensive, and we need to do this for every pixel in the raster image. And for relatively small image covering New Hampshire is a very small state. And for a raster layer with this size, exclude all those no data pixels, we still need to calculate about 3 million pixels. And memory. It has a high demand to the computer memory. And through some calculation, for example, for that very small New Hampshire raster representation, we need a 550 gigabyte memory. So on my PC, on my desktop PC computer, which is pretty high end, 2 CPUs, this much of the RAM, and this is data. This is data for birth defect study. We have this many birth defect cases, this many of all birth, and the 2 age categories, and the 20-town polygons, 100-meter resolution for the raster, and some small number for the iterations. It took 40 hours on my computer, and we already optimized greatly, because before this, I have another data set, maybe even smaller than that, a lung cancer study. It took maybe 35 days to finish the calculation on my PC computer. And we optimized the process. Now with this one, it took 40 hours. So this is why there's a high demand to computational capability, and this is why I seek to take advantage of CyberGIS. And Anand and Shawan have been taking lead on this part. So this is the integration. This is a migrating process from the PC to the CyberGIS platform. So basically, we need to first set up the infrastructure and build a user interface to communicate about the data, and deploy the programs to different CPUs in the cyber infrastructures and public application. And for the interface, this interface is the interface between the CyberGIS platform and the actual user who would like to take the approach to do the analysis, to do the spatial epidemiology analysis, and basically for communicating data, to take the data, the input data from the user and send the output result to the user. And so the interface is very important, and currently is still at a very generic stage, but we're still working on to make them more and more user-friendly. And the coding part, they're migrating my original MFC code to the Linux environment and deploy them to different CPUs and take advantage of cyber infrastructure. I'm not going to talk too much details in this CyberGIS implementation part, because I think in the second half of this morning, you guys are going to see some more detailed demonstration on this, and so I'm going to save time here, not to talk. Yes, thank you. These are some ongoing. So this back to the first slide. We have 3 functions we want to take advantage of CyberGIS, and right now we are mainly focused on the second one, computational capability, but the first one, the third one, also very important for this spatial epidemiology application. For example, we would like to have this approach to be accessible to the real public health researchers and workers so that they can take advantage of CyberGIS. They can access from their own desk to the CyberGIS infrastructure, CyberGIS analytical model to use this approach to do the disease mapping and the environmental health studies on their end. So the accessibility and the interoperability also very important. This is ongoing. This is something that's ongoing. Another very important in this very particular application is the data, because many data in environmental health study, in public health study are confidential, and we already encountered these problems. I already received several requests to see if they can use this approach, this methodology, this program to do their studies, and then when the conversation got in that there's a data problem, they cannot really send the data to me, and that's a problem. So there's an IRB problem. Sometimes they put me on their IRB, they add my name to their IRB so they can send me data. Sometimes they cannot, and basically the collaboration stopped in the middle. So this is something we need to consider in the future, the big issue, I think. There's a funding source we acknowledge and appreciate. Thank you. I don't know if I have a question. Time for question. Thank you very much.
No questions or comments? We have to be fairly brief, but yeah.
Well, very nice and interesting talk.
Thank you.
I'm interested in the p-value map. So basically, you are comparing one layer of your assignment of the accident of the diseases. The other layer is like a background information or environment.
The other layer you can consider is random. You can consider HO scenario.
Okay. It's random. So if the p-value is less than 0.05, for example, you say there is a significant relationship.
Yeah.
If it's above that, you say kind of random, yes. No.
Yes.
So
which
you
means
say
if HO can be accepted or not.
Then for that standard deviation map, you can give an uncertainty map. If the standard deviation is huge, or say the corner is dark, then you say uncertainty is high, so even though the p-value is low, you are not very sure.
That is right.
There is a good
that is right. Essentially, yes.
Okay.
Yeah, there's some technical details, but essentially that is right.
Okay.
You had a 100-meter population map?
Yes.
What was the source of that?
I generated by integrating census data and the land scan data. Land scan data from an Oak Ridge national lab.
So did you characterize the uncertainty in the land scan data?
I didn't. I don't think there's any way to characterize uncertainty in land scan data right now, but we are working on it. Yeah, actually, I'm collaborating. I'm talking to people there, to Buddha there, and I think in the next generation of land scan data, they are trying to come with some information about uncertainty of that data itself. Yes. I don't know if you have any comment on that uncertainty of the land scan data.
Well, yeah, I think going down to 100-meter resolution on a population density surface raises all sorts of semantic issues.
Yes.
Before you even start to think about the statistical uncertainty.
Yeah. Can I just one more sentence on that? The reason I chose this 100-meter, actually 100-meter, yes. Sometimes I choose 250. It's a compromise between census data and land scan data. Because in urban area, the census block can be much smaller than 100 or maybe 200.
Yeah.
But in rural area, census block much larger than that, but land scan much higher resolution. So it's a compromise between these two.
Okay.